Hello everyone, welcome to my channel. So today we are going to talk about some important topic in chemistry subject that is called reagent chemistry. So today we are going to talk about only the reducing agents like lithium aluminum hydride, sodium borohydride, sodium cyanoborohydride, etc. etc. Now here you can see here that lithium aluminum hydride, it is also known as in short form LiAlH, and which is basically acts as a reducing agent, and that is commonly used in modern organic synthesis. So there are several methods are available in the literature so that you can easily prepare this particular compound. So one important method for the preparation of lithium aluminum hydride is, if you treat lithium hydride in presence of aluminum chloride, definitely it provides the desired product like lithium aluminum hydride along with 3 equivalent of lithium chloride salt as a byproduct. In addition to that, you can also prepare this particular compound by reacting with sodium along with aluminum and hydrogen gas. It provides sodium tetrahydroaluminate. Further, the sodium tetrahydroaluminate further reacts with lithium chloride. It provides lithium aluminum hydride. Okay. So now, as you can see here, it is extensively used for the reduction of carbonyl compounds. Now, basically, if you look at here, this lithium aluminum hydride, it has two parts. One is lithium ion, another is tetrahydroaluminum part. And the structure of this particular anionic species, it has tetrahedral structure where aluminum is directly bonded with 4 hydrogen in this tetrahedral fashion, and the overall charge is -1. And as you can see here that lithium aluminum hydride is more reactive and less selective. If we talk about the organic synthesis point of view, you can see here that lithium aluminum hydride is more reactive and less selective, and it preferentially reduce the carbonyl unit, cyano unit or imine unit, ester unit, or you can say organic acid moiety, acid chloride, as well as acidic anhydride unit. Now, what is the role of this tetrahydroaluminate here? Now, in this particular reagent, here H minus, that is hydride, can act as a nucleophilic. Hydride, it can act as a nucleophilic, and normally it attacks polarized multiple bond by transfer of hydride ion to the more positive atom, and that is why they do not usually reduce in isolated carbon, therefore like carbon double bond or multiple bond, etc. etc. So it is also noted that alkali metal hydrides like sodium hydride, potassium hydride are not easy to transfer the hydride, and they can act as a reducing agent because firstly they are insoluble in organic solvent, and secondly the hydride of these types are not nucleophilic in nature, so therefore they can act as a strongly basic in nature. Okay, so now when we try to or try to react with sodium aluminum hydride, or if you try to do some reaction or reduction in presence of lithium aluminum hydride, so the solvent is very important over here. So this solvent is used for lithium aluminum hydride reduction is ether or the derivative of ether. That is very important. Now next, coming to the mechanism part. So let's say if you take any ketone substrate, you can see here, so that is the ketone substrate, and this is the anionic part of this lithium aluminum hydride reagent. So initially what happened, this hydride, it will attack over here in this electrophilic carbon. So this particular carbon center is electrophilic in nature. So therefore when it attacks over here, it will provide this kind of this tetrahedral intermediate. Now this O minus further it attach with this LiAlH4 and finally it provides this sort of intermediate. Now again, as you can see here, when this trihydride alumina or trihydride aluminum moiety attach over here, again it provides another equivalent of one equivalent of hydride ion, and further it will attack over here in this another ketone compound, and ultimately as a whole it provides a secondary alcohol product. As you can see, after acidic workup, finally you will get this secondary alcohol. So therefore from this reaction mechanism we can easily say that 1 mole of lithium aluminum hydride requires 4 mole of ketones to give 4 mole of alcohol. That is very important, as you can see. And finally you can see that in the first step in the above sequence is the fastest, and the rate simultaneously the rate of the reaction decreases in the successive steps as electron withdrawing inductive effect of the alkoxy group, that is called alkoxy group over here, oppose the loss of H minus ion, and therefore as you can see the last step is the rate determining step. So this is the last step, that is called rate determining step, RDS step, or you can say the slowest step of this particular reaction. Okay.